Hello, everyone. Thank you for joining us in this session, AI AIM380 Customized Amazon Nova Models for Enhanced Tool Calling. We appreciate you spending the time with us. There are some information sheets in front of you that tell you what kind of fine-tuning techniques and models we are going to cover in this session. My name is Harsh Asnani. I'm a worldwide specialist Gen AI SA at AWS. With me joins Anupam.
Hi, this is Anupam. I am Senior Solutions Architect in Nova team, so happy to be here and introduce the customization features that we have launched. Yeah.
Perfect. So a quick overview of the agenda. We'll go into a little bit of concepts of what model customization is, what key considerations are for model customization, especially for tool calling, so what techniques are available, what we used. We'll quickly also go over the recent re:Invent launches about Nova. And from there, we'll dive deep into the code talk, take you through some code that we've developed in this session to show you how you can enhance tool calling capabilities using Amazon Nova models. Okay. Why model customization, right? So before we dive into Nova's customization capabilities, let's get into the spectrum of customization techniques available, not just in Nova, but generally on foundation models. So it all starts with choosing if you have to modify the weights or not of the model, and you can see from the left to the right, the level of customization and effort increases when you try to change the weights of the model. On the left is a light touch technique. You could try something like prompt engineering, where you tell the model the way you want the model to respond in a particular format, but essentially the model still retains the concepts that it has been trained on. So if you have new concepts that are specific to your organization's data or the styles that you are used to, you can probably provide that in a prompt engineering text and a couple of examples, and basically just take an off-the-shelf model and see how it performs for you. You can also use RAG, which is short for Retrieval Augmented Generation. And what that lets you do is also, without modifying the weights of your model, it lets you provide organization-specific data at the time of inference. So again, if the model hasn't learned some things after it was trained, but you have in your organization's corpus, it will pick it up and respond accordingly. There are times where you will see with these approaches that you will see saturation. You'll probably see styles of responses not matching up exactly to what you need, which is where you go to the right side. These techniques will modify the weights of the model. They're divided into post and pre-training. All the way to the right is pre-training, and with pre-training, what you do is basically the use case is, if there are concepts, again, in your organization that haven't been learned in a model, you can use pre-training pre-training techniques. But if you only want to modify the model for the style of responses in a particular format, then you could use something like post-training, which also modifies the weights of the model, but is not as intense and doesn't require as many resources or expertise to train the model. So now that we've understood the progression of the customization techniques, let's get into how you can do this with Amazon AWS. Especially for Nova models, we have two offerings: SageMaker Fully Managed Training Jobs and SageMaker Hyperpod. What SageMaker Training Jobs let you do is define your training workload through declarative syntax and Python SDKs, where you provide your custom training scripts, your data, and it just takes care of everything about spinning Docker containers, bringing them down, observability, scalability, things like that. But if you're coming more from a background of EKS and you like more control on getting into your EC2 instances, SSHing into it, and you have a requirement for maximization of control, you can use SageMaker Hyperpod as well. With that, I'll hand it over to Anupam to go over some launches.
Yeah, thanks, Harsh. So we'll basically go over some of the launches that happened this year in keynotes. Primarily, first is the addition of different models that we added. So you can see the first generation models that were released last year, Micro, Lite, and Pro. Hopefully you guys played with it and using it. The second generation is something that we launched the day before yesterday, which was Nova Lite 2, Nova 2 Lite. And that is, again, a new generation model built from the scratch up with newer training data, improvements on more multilingual capabilities, more agentic use cases, more coding abilities. So it shines in those cases. There are public reports available, so you can read the technical report, which has very clear benchmarks and comparisons with other models. And then we also released 2 of the early access model, or private preview as we call it, which is the Nova 2 Pro, which is like a big brother to Lite, is a bigger model, but more better in terms of knowledge and intelligence. And then Omni, which is any to image and text. That means you can pass in any modality, and it kind of answers back either in text or the image, for example. Like kind of mixture of a Nova Pro with Canvas, for example. Apart from the base model launches, we also released something called as Nova Forge, which is basically an open training concept where you get not just the base model or the recipes for customization, but you also get intermediate checkpoints of Nova, which you can use to get started with your customization. Until now, you only could use the final checkpoint, which was the production model that everybody would have access to. But this allows you to get a mid-trained, previously trained, only CPT trained, so that you can start from various other checkpoints as well. Apart from checkpoints, we also added Nova data, which means that you can mix Nova data with your data when you are training. So there have been scientific evidences that show that when you do a mix-in between your data and the data of the LLM that it has seen when it was training, it increases the learning capability of the model. So yeah, those are some of the key value props / benefits of Nova Pro. You get access to multiple different checkpoints rather than just the last checkpoint. You can blend your proprietary data with Amazon Nova curated data. You can also use reinforcement learning by bringing your own environment, which means like we work with customers who have built their own environment where they do reward function calculation and use that to improve the model. And they didn't want to move the whole setup to AWS because you have invested and created that whole environment. So this lets you just hook up that external environment, which is calculating the reward function, while training the model in the VPC. And then, yes, it comes with the push-button recipes. So you get like pre-baked recipes with the most optimal values for multiple hyperparameters that you can use. And then lastly, you also get a responsible AI toolkit so that if you have a security use case or a content moderation use case, you can utilize and modify or customize the responsible AI layer of Nova as well. So yeah, that's pretty much the launches. This table gives you a higher level overview of the 1.0 offerings and then 2.0 offerings in terms of different techniques. Like Harsh mentioned, they are post-training. So like if you see parameter efficient fine-tuning, which is a type of fine-tuning where you are only changing the adapter of the model, as well as full rank fine-tuning where you're changing actual weights of the model. Both are available in 1.0 and 2.0. DPO is another kind of post-training where you are getting like that thumbs up, thumbs down feedback, and you want to teach model what a good looks like versus what a bad looks like, so that it can steer towards your preferences or human preferences. That is also available in 1.0, and similarly PPO, which is another class of, very similar to DPO, but another class of RLHF technique. And then we have reinforcement fine-tuning, which is the state-of-the-art RLHF as of today, which is available in 2.0. And the reason why it is only in 2.0 is because RLHF works, or RFT, which is reinforcement fine-tuning, works much better on a reasoning model. And Nova Lite 2 is a reasoning model. So that's why that combination. With that, we will jump into the use case and just give you a brief idea of what we are going to do today. Rather than spending too much on PPT, we'll move to code now. So the use case architecture that we are going to pick today is a security agreement legal assistant agent. So this agent would be responsible for looking through the multiple documents, and then we will give it a question, and it has to pick the right tool to call to get access to the right information, right parameters to pick, and then go from there. So in different modules that we will cover, firstly, we will teach you how synthetic data generator works or how you can generate your own data, because we see a lot of customers who don't have the data to begin with when you come to customization, and that is like a P0 or prerequisite. So we'll give you some sneak peek on what synthetic data generator we have been using for this particular demo. And then do a base model evaluation just to get, okay, where we are from just the base model without any customization. Move on to supervised fine-tuning. That's the first thing we would use for fine-tuning with prompt response pairs. Do a eval on that post-SFT checkpoint to get, okay, how much did we improve from the base model. Move on to reinforcement fine-tuning, which would be sitting on top of the SFT checkpoint. So it is an iterative fine-tuning approach. And then do a post-RFT evaluation to see how that goes. And then finally, make a deployment to Bedrock to make inference. So we'll cover all these modules in today's code talk. We have very 1 hour, but too many modules to cover, so hopefully we are good there. But just to give you an idea of what SFT is, if you are not familiar with it, it all starts with an adapter trainer if you go with the LoRa-based technique or parameter efficient. That is what we will be showcasing today. It's the most lightweight SFT you can do with like limited resources, quick, you don't really have a lot to spend, and you get decent results in the first go, or at least give a good signal if the model is capable of learning for your use case or not. So adapter training basically gets the data from your database, which could be S3 in this case. It gets the base model from the recipe, and then it basically do a forward-backward pass to learn from the data that you're providing along with the base model, and gets a trainer, and then you get the base model, and you do a fusion where the adapter is fused with the base model to get the final model. So that is what SFT does essentially. SFT adapter-based training does essentially. It's just a light adapter that you're training and then doing a fusion. While RFT is a little more elaborate, so it has training VPC, customer VPC. So in training, there are two main modules. There is a rollout and there's a trainer. And then in your customer account, there is the Lambda function, which is the reward function. So again, you get access to the prompt data, which is your data set that you want to train the model to teach the RFT technique. And you get the base model. You, again, load both things from the rollout, and trainer also loads the base model. And then it calls the Lambda function to calculate the predictions. So what does rollout do is, think of it like I don't know, a system that generates like n number of answers. So rollout is like n number of generations or n number of predictions, and passes all those n predictions to the Lambda to calculate the score based on your evaluation metric. It gets the responses back, which is basically rewards. So it gets the rewards back, and then it feeds those rewards back to the trainer. So trainer can learn from those answers or from that feedback and further improve. And then it does the forward-backward pass on the trainer to get the learnings, and that's where it goes back to the rollout to update the weight policy. And this cycle continues where more rollouts are generated, Lambda function calculates the rewards, passes it back to trainer, trainer updates the weights, new rollouts are generated. And that cycle continues for n number of steps that you define in your recipe, and that's how the model starts learning. And we'll see today how it happens in real example. Okay, with that, I will move on to the code sample. So yeah, let me switch.
Okay, so time to dive right into code soup. So this is a code talk. There's a bunch of code we've developed to demonstrate the use case. Planning to get through all of it in an hour, but it can get dense. So we have planned to show you the essential code blocks and hide away some of, or glance over some of the utility helper functions. We will take questions at the end of each notebook, maybe a couple. We'll do a quick time check, and if there are more questions, we can just probably take them out in the hallway. This is not a demo, and we want to keep this session educational and interactive, so please let us know if you have any questions at the end of the notebooks. First up is the data prep step. What's interesting here is that instead of taking an existing data set, we have generated data to fine-tune the foundational models for an example use case. essentially just pulling it out of thin air. And the idea is that if we can generate this data from silos, anywhere on the internet, data that is structured, unstructured, or a combination, and create agentic AI applications that are hyper-personalized, you can do the same with data existing in your organization's silos. Coming back to the use case that we have here, there are 3 data sources that we use, and imagine that the end user is an attorney or a paralegal or someone who's trying to ensure securities transactions like private stock sales, public offerings, comply with SEC regulations. We do want to point out that you can use NOVA models for a variety of use cases, but especially for legal and healthcare use cases. Please use it at your discretion, and especially with other regulated and sensitive use cases as well. But here we have 3 data sources. So we have the Edgar filings that are the actual agreements that were filed with SEC themselves. So a paralegal or an attorney filled the form out, push it out for review to SEC. Then there are the SEC formal language regulations that tell us how to, the legal language that should be in those agreements. And finally, there are judicial interpretations from federal judges and courts of those filed agreements. So the model can use these interconnected data sets to enable cross-document analysis and validate the agreements against the text that's required, the text that provided, and how the text was interpreted. So we will glance over some of these functions. We will also publish these in a GitHub repo soon, so you will have access to everything that we covered here and more. But these are just basically crawling some data from open source websites. These can be easily modified to download the kind of forms that you want to download, for example. Then comes the actual synthetic data generator, and once we do have the raw data sitting with us, we can start generating data in a format that is ready to be consumed by NOVA, the NOVA models that we'll use. The format will depend on the model that you use, and we recommend using NOVA, but you can try this with any other models available on Bedrock or SageMaker. Important to note is prompt engineering that should be provided while generating the data, so the model knows what format to generate that in. A quick animation shows you how that is happening. I will give it about half a minute for it to play. So you see here on the left that we have a data generation kit, and essentially what you see here is happening is chunking the data. Maybe we can actually go to a still. It's chunking the data into a predefined set of character limits. That is done because if generally data in silos exist in like gigabytes or terabytes, and this will blow up the context size of your model, and it will not be able to generate any data. So we chunk it, and the chunk size depends on the context window of the model that you choose. Again, M is the parameter. Another parameter is N. What N does is it defines the number of overlapping characters between those chunks so that the model knows if there is semantic continuity, if sentences cut midway. The model is instructed in its prompt to say that you will receive chunks of data. This is the context. Try to maintain semantic similarity. Each chunk is actually then fed into the prompt, and that makes a single invocation into a teacher model. For our use case, we use NOVA Premier. So if you have 100 chunks, you will have 100 invocations that finally generate synthetic data. We have it in a format that's consumable by our student model, which is NOVA Lite. And we fine-tune it, which we'll see in further notebooks, to be consumed by end users. Quick glance over how the format looks for NOVA, all NOVA family. For SFT particularly, you have a system prompt where you define what you would want the model to do or the agentic application to do. Here, for our example, we would say something like, you're a helpful legal assistant. please help me ensure that my agreements are to point. We can look at an example of how that is after generation. It is a bit different for RFT, but concepts are the same. You have a system prompt, you have a user prompt that actually feeds in the query, and you have an answer that is generated by the model. These are all JSON objects, so we explicitly instruct the model to generate it in that format. But as you all know, foundation models are non-deterministic in some form. So we do provide a validation loop to ensure that these can be consumed by our underlying model. Ultimately, our goal is for this model to select the right tools given an input query. So we measure what good looks like by measuring some metrics about the tools that it selected. So given a query, did it select the right tool? If it needed multiple tools, did it select it in the right sequence? The tools are essentially Python functions, so they take parameters. Did it provide the tool the right parameters that it needs to perform the query? So these are some metrics that we are tracking. These are customizable. You can provide your own metrics as well, and we'll look at that in code in a second. But for now, let's look at the prompt that we provide to the synthetic data generator. You'll see some annotations here. You'll see double hashes, guidelines, and caps. Each foundational model has prompting best practices. So for Nova, this is what it looks like, and we've incorporated it here. We tell the model what it needs to do in the prompt through these annotations. We tell it what tools it has access to and what it needs, what each tool needs as a parameter. We also tell the model to classify each query into 8 predetermined categories. So those then finally map to what tools it will use. There's a table that I can go over that shows how that works. Basically, if it's a regulation definition, this is the tool that should be used. If it's a regulatory compliance analysis, 2 tools should be used in this sequence. And finally, we tell the model that we want strictly JSON schema that adheres to this structure. We also provide some example definitions, essentially doing few short prompting in this of how the data should look like. And finally, at the end, we insert the chunk that was generated by the synthetic data toolkit. The toolkit that we used in this session is an open source toolkit by Meta. It's called Synthetic Data Toolkit. Again, you can use any open source framework for this, but essentially what we've done in this code is provided the capability to use Bedrock and SageMaker models with the toolkit to generate this data. From there, we turn the kit on. We try to do a system check. We use the Nova model hosted in Bedrock. We provide an input prompt that just says hi, and we can see the model is ready to take invocation requests. After which, we just basically file parse the data and then start generating prompts. Once that is done, maybe we can get a quick sneak peek of how that looks like. We combine it into a JSON lines file, because that's how Nova expects us to provide it for SFT fine-tuning. We also split it between 3 sets. So for example, Nova generated this query and what an appropriate answer should look like. So we further feed it to the student model, and it learns how to do this on actual user queries. We'll pause here before going to the SFT notebook to see how we do the actual fine-tuning and take any questions.
Sorry. The GitHub is public or not? Is that your question? It's not yet public, but it would be public by today. So yeah, it would be available in Nova Samples GitHub. Yeah. Any other questions? Yeah. You need mic?
Do you apply a similar process to Novasonic, or is that down the line?
You mean customizing Novasonic? No, that's not available as of today. Yeah. Maybe in the future, if there's a use case we can talk about where you're thinking of custom. Okay. Okay, if there are no further questions, maybe we can move to the SFT.
Perfect. So as Anupam told you about SFT, the magic with LoRa and SFT is that when you use an adapter trainer, which is a parameter efficient fine-tuning technique, it essentially takes 1 to 2% of the model weights and tries to fine-tune those instead of the whole model, which reduces your infrastructure, training time, costs, everything. We've seen that if you give it pertinent data, it gives you up to 90% accuracy performance as compared to full supervised fine-tuning. So basically, the adapter is the 1 to 2% of the weights that LoRa extracts, trains it, adds it to the base model, and finally gives you a fine-tuned Nova-Lite model. Since we've covered a bunch of that, let's get into model fine-tuning code. The first thing we do is set up a SageMaker session so that we can interact with a SageMaker client, submit jobs from our local notebook, provide it the data set that we need to. We select the particular instance that we will need. We also do distributed training here, so we select 4 instances so that training is faster. We select the image URI, which is a Docker image hosted in ECR. These are sticky with the model that you'll use. So if you use Nova 2.0, that will have a particular image URI. From there, excuse me, we use recipes, and recipes, as Anupam let us know earlier, are just abstractions of configurable parameters. What that looks like is let's say you want to define your training hyperparameters, the number of steps you would like to run, your learning rate scheduler, the kind of learning rate adapter you would like to use, if you would like to use LoRa or not, and then LoRa specific fine-tuning hyperparameters as well. Once that is done, we select what we call in the SageMaker terminology an estimator. We use a PyTorch estimator because Nova essentially trains this using the PyTorch Lightning framework. We provided, again, whatever variables we defined earlier, and we give it the recipe, and finally we give it the image URI, the data that we generated in the previous notebook, and start training. So this is a completed notebook, just to show you how it looks in the console. From here, you can look at some metrics about the infrastructure utilization, look at logs. You see one log stream each for each instance that it trained on. Which exited each with a status 200 code, which means training was successful. Okay, so training takes anywhere between 20 to 40 minutes. Typical workflow, ML workflow is after you're done with training, you want to look at training validation curves. So we download the model tarball of the fine-tuned data, extract it, which has a manifest file and a train loss file that tells us how the model converged. As you can see from we gave it 100 steps, but from step 0 to 100, it converged from 70 to 10, which is pretty good performance on the train set only. Now, one thing to keep in mind is this evaluation metric is actually different from our evaluation metrics that we want to test the model on, because we actually want to see what tools it selected, the series that it selected it in, and if it was JSON parsable, things like that. So the training curve is just telling you if it matched the same output that was in the training data, which is essentially what the assistant responds with. So it's a text-to-text match. If it was a match, the training loss converged. Okay. So from there, we are measuring the accuracy of tool selection by a couple metrics here. Some are traditional classical accuracy metrics. So you see precision recall F1 on tool, which is if how many times was the tool selection done properly, how many times you saw false positives, and what the AU-ROC curve looks like and what F1 looks like. We also have an overall score that is weighted based on the parameters that were provided to the tool, the tools that it selected, and the sequence that it selected in. These are customizable. One thing that's different between the evaluation that happens in the training loop versus what we do is in the eval loop, you have this test split that was sent to the base model, and then it was sent to the fine-tuned model. The way we evaluate these metrics is we have predefined functions that are loaded in Lambda. So on each invocation of the base model, as you see on the left, the answer goes to a Lambda function. The Lambda evaluates it for customizable functions and sends those metrics back to the base model. It does that for the fine-tuned model as well, and at the end, we just compare the both. Base model eval and fine-tuned model eval look very similar to a training job. So you select instance types, counts, the image URI, which is different than the training loop. You configure recipes again that point in the recipe. It points to the Lambda ARN of the Lambda that we have just configured. We define the PyTorch estimator just like we did. We provide it with the test split, start the evaluation job. Takes about 20 minutes. From there, we want to download the tarball again and look at what the results are visually. Maybe zoom out. Okay. So these are metrics on the base model itself. It wasn't fine-tuned. We'll have similarly for the fine-tuned model, going significantly up, and then we compare. So you can see overall score has jumped from 44% to 75 on the SFT loop. This is where we end the SFT cycle. We take this SFT fine-tuned model and then further try to increase its accuracy by doing RFT.
Okay, so now that we have customized adapter, let's move to the RFT, which is a cool part of it. So in RFT, as I explained, it's basically doing a rollout, which is going to generate n number of responses, and then a trainer, which will take the feedback that is coming from the reward function, which is a Lambda, and use that feedback from that reward function to update its weights, improve itself, and then do that cycle multiple times. Again, that multiple times can be defined in the steps, which is a recipe parameter. Number of rollouts that you want can be defined in the recipe parameter. So those things are hyperparameters that are configurable. So first, just the basics, setting up the IAM role, doing the imports, retrieving the two main things from Harsh's notebook, which was the checkpoint after SFT, because that would be needed to run RFT on top of it, and the results that he showed that are captured in a data frame. So yeah, for data prep, this is the format for RFT, system, user, and reference answer. Reference answer is basically anything. You can pass in any random thing which you care about, which the model should learn. It does not need to be the ground truth only. It can be thinking, notes, whatever you have, because RFT is the essence of it is that it will just learn from whatever you are passing with it. It will not memorize the ground truth only, which is what SFT does. And then we will create the data sets in that format and store it in S3, and then create our Lambda function, which is the reward function. That is the critical part in getting a good RFT, is getting a good reward function. If your reward function is biased or can be easily hacked, then RFT will go for hacking the reward function. And by hacking, I mean it will try to find loopholes in your reward function to make it maximize the reward, and then your model will just not learn that well. So it's essential to see how we created the reward function. So it's firstly so it's Lambda handler and Lambda grader. In the Lambda grader, you get an input as this, which is, so in this case, you see we passed the user prompt assistant response that came from one of the predictions, and then the reference answer, which is sort of our ground truth. So we pass like what type of information is needed, and what tool you should be calling, what parameters you should be using for that tool, and any reasoning why you picked that tool. And then it returns back aggregated reward score. Now this is a score that, because RFT works on a numerical reward function, so at the end you have to return a numerical value which it tries to optimize on. So aggregate reward function is right now is the weighted average, as Harsh mentioned, on all the metrics that we care about, like is the right tool being called, is the right parameters being used, is the sequence of the tool correct, is the JSON schema parsable, and we kind of aggregate that through this weighted average. So yeah, this is, so these are the metrics, default values, 0 if some error happens or something, but more values if things are right. And then we capture all the metrics here and the aggregate score at the end as well, and we pass the result back. So that's pretty much what reward function is doing. The main thing is you should make it gradient in your reward function. It should not be binary like plus, minus, or true, false. It should have a gradient like this is good, this is average, this is close to good, so that it uses that information to optimize close to good to closer to the best answer. And then next we create the Lambda, deploy the Lambda on AWS, and then kick off the RFT. So this is the crux of everything. So here we are passing the checkpoint, which was trained. We are passing our recipe. We are passing the image URI, which is publicly available. We are using P548X. 4 instances are minimum that are needed to run RFT. We will be using Nova Lite 2 as the base model. And then we kick off a RFT job. So again, the PyTorch estimator call, very similar to SFT, defining your train data, validation data, starting the .fit command, which is basically what will kick off the training. And you can see the logs. So you can also print the logs in Notebook, or you can go to console. But you can see the log, start seeing the steps that it is training on and all the different metrics that it is capturing. And this is a screenshot of like how the console looks like. So you can see it starts training, downloads the image, and then begins the training. Next, we capture the training results because we need to see how the metrics looks like after RFT. So in this, we get the results, which is the stepwise training metrics to see how the training is doing. And this is a screenshot of a previous run that I did. Instead of 5 steps, I did 150 steps just to see how much I can stretch it. And then I looked at the train reward metric, which is the key metric that we should be looking for RFT, like how is our reward improving? We want to see a gradual increase in reward from like a low value to going as high as close to 1. And that indicates that model is learning as the cycles are going through and the reward is improving. So in this, we see a decent lift from like 0.81 or 82 to 0.8586 in a gradual increase. It even reaches 0.9 in some cases. And that is closely correlated to the eval metrics. So what we were seeing on SFT, which was around 74, 75, it's now reaching around 88, 89 after RFT. So that gives confidence that reward functions are increasing, and we also see the entropy is reducing, so it's getting more deterministic as well. And then how we evaluate, we again do two evaluations, one on the base model RFT, and then second on post-SFT, post-RFT eval. So again, the recipe looks like this for RFT eval. You can define your inference parameters. One cool thing is that it also supports log probabilities. So you can actually get probabilities of tokens that are being predicted, and you can use that to calibrate your answers, or if you have a classifier, you can use that to calibrate what's your precision recall boundary is. And then in your RL environment, here I am passing that lambda function that would be used for evaluation as well, which is same as the reward function. So I basically kick off the PyTorch. I override those parameters because my reward function right now is just a random string here. So I'm overriding it with actual ARN of my lambda function, and I'm passing the final checkpoint that I got. So this is post-SFT eval, which is similar to what Harsh showed as well. And then this is post-RFT eval. So next what we do is we again unpack the post-eval results, and we kind of find, like, it comes in a dictionary, it's a JSON file. So we get these custom metrics from there that we were calculating in reward function as well, and create a dictionary so that we can compare in like a matplotlib using the data frame that we loaded from the last call. So this is how we see it. Like the base model was 0.44 on this task, fine-tune made it 74, RFT made it around 90. So that progression tells us that it is improving if the RFT is introduced at a later cycle than SFT. We also tried to switch this up, like doing RFT only on the base model instead of doing SFT first, and we didn't see that good results on that. And that indicated that SFT is actually helping with RFT because SFT is getting the basics right, getting the formatting right, JSON schema right, all that, and then RFT is improving the quality of the parameters that are being predicted. This is more results on a different different metrics. This is only on overall score. That is what we care about, but these are the sub-metrics and where we see it failing the most, or we can still continue doing it, the failure analysis on it, and improving our RFT data to see further improvements if we want. But that gives a good indication of how you should be doing, like starting with your base model eval, SFT, and then post SFT, RFT. But the good part is like you can keep continuing these iterative loops. So you can keep building on top of a previous checkpoint and saving that checkpoint, evaluating that, and then building on top of it. The last notebook that I wanted to show is the deployment. Now that we have the final checkpoint. So final checkpoint goes as a S3 URI. So you don't get the model itself, you just get a S3 URI. If I can find an example here, let me show. This is the checkpoint S3 bucket that gets loaded, but I can find, let's see. Like for example, this is an example of how a checkpoint would look like. This is a bucket which you will not have access. It's a service-side bucket, but that checkpoint can be accessed through the IAM policy that you will be using. So this checkpoint is now our task is to take this final S3 checkpoint from after RFT and somehow move it to Bedrock so that we can make inference calls. And that is done through two Bedrock functions. So basically what we will do is first we will export the model from S3 checkpoint to Bedrock. So with that, we will use the create custom model API, which will move the model to Bedrock. We will monitor the status of it. Once it is active, that means the model is deployed on Bedrock. And then we will make it the second call, which is using create custom model deployment. Now, this will use on-demand inference and basically create an inference endpoint for you of your custom model to start hitting on Bedrock. And this is, again, because we used LoRa across the thing, like we did SFT on parameter efficient, we did RFT also on parameter efficient, we can use on-demand inference because everything was on adapter only, so it can reuse the same hardware. Yeah. And then we finally see the model in Bedrock, which is now hosted, and it can be made to hit publicly through your AWS account. So how do we change code when we are making the inference call? It's basically one line of change. So this is a Converse API, which all you might be familiar with. Here I'm passing the model ID as base model, which is Nova Lite 2, and I just get some random results of like explanation, which is useless to me because I was asking it to be structured output. And then I did the same call, but this time I passed the deployed model ID, which is the ARN of the on-demand inference that I got from the previous call. And here I get much structured answer with the right tools being called, like the statue retrieval and then compliance checker. So that indicates me that the model has learned and it's improving its accuracy from the base model. So that's pretty much it, what we wanted to cover end-to-end from data prep to SFT to RFT and then deployment. We're open for questions if anybody has any.
Yeah, we'd love to talk about use cases that you have as well, since we have some time, if you wanted to discuss those, but yeah.
Awesome. Cool. If there are no further questions, you can scan and give ratings or whatever what's called.
CSAT?
CSAT, yeah.
CSAT, yeah.
So you can give it.
Helps
so,
us.
Yeah, but thanks for attending the talk.
Yeah.
And we'll be hanging out here, so if you have any questions.
Thank you.